This is an AS Mechanics question on velocity time graphs. A train travels along a straight horizontal track between stations A and B. In the model of the motion, the train starts from rest at A and moves with constant acceleration 0.3 meters per second squared for 80 seconds. The train then moves at constant velocity before it moves with a constant deceleration of 0.5 meters per second squared, coming to rest at A. Part A. For this model of the motion of the train between A and B, Part I or Part 1 of Part A, state the value of the constant velocity of the train. Now we can use SUVAT to answer this question because it's constant acceleration. We're told that the train starts from rest at A. We know the acceleration for the first 80 seconds. And we also know that it moves with a constant velocity and then there's a constant deceleration. So because this acceleration deceleration is constant, we use SUVAT. So if I write my letters out, S, don't really care about for this part of the question. U starts from rest, so U is 0. V is what I want to find. A, this constant acceleration, is 0.3 and the time is 80 seconds. So with these values, I know that I'm going to be using V is equal to U plus AT. So V is going to be 0 plus 0.3, that's A, times by T, which is 80. And that gives me a value of 24. And that's meters per second. So that's my first part of Part A. Then the second part of Part A, I need to state the time for which the train is decelerating. Let's write down second part, Part A here. So here we can use SUVAT again. It comes to rest at B, so that means that V is 0, the final velocity. The velocity before is what the constant speed was, or the constant velocity, that's 24. I have a deceleration, so this is going to be negative 0.5. And I want to find T. So that's V equals U plus AT again. V is 0, U is 24, A is negative 0.5, that gets times by T. So that's 0.5 T is equal to 24. If I times both sides by 2, I'll get T is equal to 48. That's 24 times by 2, and that's 48 seconds. So that's the second part of Part A done. Now the third part of Part A says we need to sketch a velocity time graph. So we will have a velocity axis, V, and we'll have a time axis along here, T. Now it just say a sketch, so I don't need to ensure my scale is super accurate, but I'm going to try and do that and maybe use the correct amount of squares just so you get an idea of the shape. So I'm going to go up in 5s, I think, on the velocity axis. Now when it comes to the time, I know the amount of time is accelerating 80 seconds and the time it was decelerating 48 seconds, but I don't know the time at which it was moving at a constant velocity, so I'm not really going to be able to fill this in completely. So I'll put in the time for the acceleration here, and the time for the deceleration is just going to be 48 seconds. So all I know is that it's 48 between those two, but not the actual values. So let's start with the first bit, the acceleration. It accelerated up to a speed of 24 meters per second in 80 seconds. So we got up to around about a point that's here. So let's try and draw in a straight line like that. And then we had this constant speed up to this point here, and then it decelerated a little bit more there. It decelerated from that point where I've marked the 48 like this. Still not getting that completely straight, so let's try this. That'll do. And then we're decelerating back down towards this point here. And I guess the most important thing is the shape. Let's just do a single line there, like that. And the shape is what is important, and really I guess that the second line down here needs to be steeper than the line going up, because the deceleration is greater than the acceleration. So it's important that you get the steepness of the lines correct, even if we don't have any values on the scale. The total distance between the two stations is 4,800 meters. Part B, using the model, find the total time taken by the train to travel from A to B. I've got my velocity time graph from part A, and if the total distance between the two stations is 4,800 meters, this area is equal to 4,800 meters. So when we've got a velocity time graph, the area under that graph is equal to the total distance, so 4,800. Now what I've got here is a trapezium, so I want to be able to find the area of that trapezium, make it equal to 4,800. Do I know the height of that trapezium? Yes, I do. That is that constant velocity, which is 24, and I need the lengths of the two parallel sides. Now I know the lengths of these n bits, but not the total length. So what I'm going to do is to call this bit in the middle t, so this length here, which means I can also write the length of the bottom in terms of t. That's going to be t plus 80 plus 48, and that is 128. So the length of the bottom side is t plus 128. So now I've got the lengths of my sides, I've got the height, I'm going to set that equal to the area. Now when we do these types of questions, we just want one unknown, so don't use one letter for this length and a different letter down here. You're not going to be able to solve it. Right, so the area of my trapezium, t, that's the top side, plus the bottom side, t plus 128, over 2 times by the height, is equal to the area, 4,800. We'll start by dividing both sides by 24 and simplifying this top part of the fraction. That would be 2t plus 128 over 2 is equal to 200, dividing both sides by 24. If I times both sides by 2, I'll get 2t plus 128 is equal to 400. Next we'll take away 128 from both sides. That will give us 2t is equal to 272. Divide both sides by 2, and that gives us t is equal to 136. Now this value of t is just the length of this bit, or this bit in between. We still need to add 80 and 48 to get the total time from A to B. This t only represents the time that it was moving at this constant speed. So our final value for the total time between A and B, so 136 plus 128 gives me 264 seconds. Part C suggests one improvement that could be made to the model of the motion of the train from A to B in order to improve or to make the model more realistic. So I've got two suggestions here. One is that we could use variable acceleration or deceleration, or both, rather than a constant acceleration or deceleration. That'll make it more realistic. That would actually mean that these wouldn't be straight lines anymore, they would be curved. And my second suggestion would be to have a smoother transition or change to and from the constant velocity part of the journey. Now what that would do, that would round off these corners and probably have something a little bit more like this, where it'd be rounded rather than this sudden change from a acceleration to a constant speed and then a sudden change from this constant speed to deceleration.